This video introduces you to the laboratory exercise called centripetal force. This is a laboratory exercise that you can do at home. For those of you enrolled in Physics AB, Honors Physics AB and AP Physics C, this will then be ultimately turned in as a laboratory report following the format for such reports. Okay, let me take you through the purpose and theory behind this exercise. Okay, so this is our lab on centripetal force. Okay, the purpose here is going to be to verify F equals mv squared over r. That is Newton's second law for situations involving, for example, uniform circular motion. We're going to do so by using a conical pendulum. Okay, now there is some theory behind the exercise. The theory behind the exercise is a problem that I did in a lecture, specifically the conical pendulum problem. Now recall the basic setup of that example. We have right here, for example, the conical pendulum itself, a mass m, and the string has a length L associated with it. We then begin to break up L, like so, into components, where right here is the angle theta. Okay, and then recall that the circle itself is perpendicular to the board. The pendulum is circulating out of the board and into the board like so. So let me draw that as an oblique circle like so. Okay, and then right here, for example, is the centripetal acceleration vector, a sub c, inwards towards the center of the circle. And then in the course of that problem, I derived the following expression for the period. I did so by using F equals ma. The period is equal to the following. Okay, now even though I'm not redoing the derivation here, I've already done it in class. I've already done it in lecture. However, you must reproduce the derivation of this expression in the first section of your laboratory report. I will be looking for that derivation specifically. Make sure that you show that derivation completely, ultimately arriving at this expression here. And now here's the basic idea behind this laboratory exercise. For pendulums of various length L, what you're going to do is measure the period, for example, with a stopwatch. And then ultimately, if you measure this, and this is a known quantity, then we can measure G. So by measuring G as 9.8 meters per second squared, we then verify the purpose of this experiment. And the reason for it is because this equation was derived by using F equals ma as our starting point. Okay, now what I'm going to do here mathematically, however, is I'm going to back up one step in the derivation. I'm going to go ahead and square both sides of the expression. When I square both sides of the expression, I then end up with this. Like so. This is the previous step. And then ultimately, when I get to the procedure in just a few moments, here's essentially what you're going to end up doing. For various pendulums of length L, you'll measure the period, capital T, with a stopwatch. And then what we'll do is we'll plot, we'll graph T squared versus L. When we do, think of this as the equation of a line. Think of it as y equals mx plus b, like so. So then therefore, because you'll end up with a line when plotting T squared versus L, the slope of the line is what I've written here in parentheses, 4 pi squared over g. So once we get our slope, we'll set it equal to this quantity here, and then from there we'll calculate what g is equal to. Okay, with respect to the procedure, however, if you're careful in this exercise, you should get really good results. This is actually a very easy way of measuring G. It's much easier to do than doing, say, a free fall lab like we did during the unit on kinematics. Okay, let's go ahead and get to the procedure. Okay, now you can do this laboratory exercise at home with a couple of very simple pieces of equipment. First of all, you're going to need a blank sheet of paper. You're going to need a drawing compass. You're going to need a ruler. You're going to need some scissors. You're going to need some string. And you're also going to need a small object. You're going to need a small object such as this washer, for example, where we can tie a length of string to the washer, to the object itself. So with respect to the procedure now, what we're going to do is we're going to start with an L equal to 0.2 meters. Now the distance L is going to be from where I pinch the string with my finger, I'll demonstrate in just a few moments, to the center, the geometrical center of the washer. That's going to be the length L. Use whatever it is that you're using as a pendulum. Well, measure the length L from where you pinch the string with your finger to the geometrical center of the washer. So let me go ahead and demonstrate. I'm going to go ahead and cut a length of string like so. I'm going to go ahead and tie it like this to the pendulum, to the washer that is. Like so. Once again, you want to find a small object that you can easily tie the string to. You may have to be a little bit creative with that, depending upon what materials you have at home. But a washer works very well, like so. Okay, and now the distance L. That's going to be from where I pinch the string with my finger to the geometrical center of the washer. All right, so 20 centimeters from the geometrical center of the washer to where I pinch the string with my finger is this distance right here. Notice that I have a little bit left over like so. Make sure that you move this off to the side because that's not going to be part of your pendulum. Okay, now what we need to do is we need to manipulate our pendulum into a circle. We're going to do so by drawing a small circle here with the drawing compass. What I'm going to do is I'm going to measure out a distance here on the compass only equal to 5 centimeters. So I'm using my ruler to do that, like so. And now I'm going to go ahead and draw a circle here like this with a radius of 5 centimeters. Okay, this circle that I'm drawing here is then therefore going to act as a guide when I then manipulate the pendulum in the uniform circular motion. Your circle, by the way, doesn't have to be perfect. It just has to be used as a guide like so. Okay, so we're going to draw a circle with a radius of 5 centimeters. And we'll do so as I did on a blank sheet of paper. And now what you do is you hold the piece of paper on the floor, or rather just put it on the desk, that is, like so, and you then have to manipulate the pendulum such that basically the pendulum itself is following the circle that you've drawn on the piece of paper. So you're using the circle as a guide. The easiest way to do this, by the way, is to stand above the pendulum as I'm doing here. Don't hold it to the side. If you hold it to the side, you have a tendency to wave your hand around. And then what you want to do is you want to kind of get the motion as I'm doing here, like so, such as your pendulum is basically following the circle. And then very carefully with a stopwatch on your smartphone, measure the time necessary for 5 revolutions. If you're going to count out loud, what you want to do is you want to start the clock when you say 0, and then 1, 2, 3, 4, stop at 5. That will then ensure that you counted 5 revolutions and not accidentally 4 or 6. So you then measure the time necessary for 5 revolutions. Okay, we're going to call this small t. And then from there you can calculate the period, big T, which is that time divided by 5. Then you start to construct the following data table. Your data table is going to have the following columns. First of all, the length L. This is in terms of meters. Then the time small t in seconds for 5 revolutions. Big T, the period, also in terms of seconds. And then when we eventually get to the graph that I mentioned a little while ago, we're eventually going to need a period squared, like so. So whatever it is that you calculate here for the period, you just square it here and then place it into this column on the data table. You're going to do this process for pendulums of lengths 0.2 meters, 0.4, 0.6, 0.8, and 1.0. So when you eventually get to a long pendulum, you would then probably want to take your piece of paper and put it on the floor like this. Okay, and then I just have another pendulum here from earlier. It's already pretty long, like so. And then you take your long pendulum and you stand above the circle like so, and then get the motion here of uniform circular motion as I'm doing here, and then once again measure the time for 5 revolutions. If you need to employ an assistant, a family member to assist you in doing this, particularly in measuring the time, then by all means do so. You may want to do, by the way, the process a little bit backwards. You may actually want to start here at the bottom of the data table with a length of 1 meter and then cut the string appropriately like so until you eventually get to 0.2 meters, 20 centimeters. That just might be an easier way of doing it. Okay, once you have your data table filled out, then you then plot the following graph as I mentioned earlier. Okay, so on a piece of graph paper, you then plot the period squared as a function of the length L in terms of meters. When you plot your 5 points, you'll have to scale your axes appropriately depending upon your data. When you plot your 5 points, it will very obviously be linear. What you then want to do is take a ruler, fit it up to your points, and draw a best fit line. Like so. And then for that best fit line, let's go ahead and calculate the slope and call it m, as in y equals mx plus b. Now here's what your slope should equal. Your slope should equal 4 pi squared over what we'll now call g experimental, like so. So then what you want to do is you want to cross multiply and solve for g experimental. So just to clarify, your slope is not g experimental. Set your slope equal to what it should be, which is 4 pi squared over g experimental. Cross multiply and then solve for g experimental. Of course, it should be equal to 9.8 meters per second squared. So the last thing to do then, therefore, is to just calculate a percent error. So your percent error is going to be the absolute value of the difference between g experimental and what it should be, which is 9.8 meters per second squared. Divide then by g, 9.8 meters per second squared. You'll end up with a decimal here, multiply it by 100 in order to convert it into a percentage. As I said, if you're careful, you should get really good results. Make sure that you measure the length L carefully. Also make sure that you measure the time small t for 5 revolutions carefully. If necessary, make sure that you employ an assistant in helping you complete this exercise. Once again, this exercise is a formal laboratory report. There are additional instructions for you in the folder for today.